Okay, for 14.2, not very difficult, and you've already learned all of it in the gas law simulation worksheet that you did. If you are having a hard time with those relationships, you can listen to my explanations. Otherwise, I suggest trying to fill in the slides. For example, for Boyle's law, try to fill in the graphical relationship between pressure and volume. Try to think of an example and try to fill in these blanks down below. Okay, and if you want to pause and do that and then check your work with my work, you can. So a good example of Boyle's law is a syringe, because you can have a sample of air that's at a constant temperature, but when you pull out lock the syringe or plug it and pull out the back of the syringe or push it in, the pressure inside changes as the volume changes. So you can kind of imagine that if you in order to increase the pressure inside the syringe, you have to decrease the volume. So you can see that if down here, if pressure increases, that's because volume has decreased, and conversely this, which means that they are inversely proportional, which means that when one, like for example up here, if volume is large, that means that pressure is low, right? And if volume is low, that means pressure is high. So you get this curve that looks like this to show the relationship between them. That's an inverse relationship. Okay. Moving on. Oh, if you're trying to remember Boyle's law, my mnemonic device for this is that Boyle sounds like it would involve temperature, but it doesn't. So if that helps you, that's great. If it doesn't, that's fine. Charles's law, volume and temperature. So a good example of this is a balloon. And it's a little bit of a tricky example because if you think about taking a balloon from a cold room or even like from the classroom to a cold day, the balloon would shrink. And there is actually a transitional period where the pressure inside the balloon is changing. However, by the time the balloon settles on a final volume, its pressure has equilibrated, so to speak, with the outside pressure. And so, thank you. So the pressure at the beginning and the end is a constant, even if during the transition it changes. Okay, so you can see that when you take a balloon outside and the temperature gets colder, the volume also gets colder. The reason for that being that the particles move more slowly, they collide with the walls of the container less often and less forcefully, and they decrease the pressure in the container, and then you have this moment in your balloon where you have lower pressure inside than you have outside, right? And how does the balloon respond to that? It gets smaller, and in getting smaller, its internal pressure actually increases because you decrease the area of the collisions, the surface area, and eventually you get to a point where it's a smaller balloon, but the pressure inside is now equal to the pressure outside. And so it stays at that volume. You have to have something with a flexible volume in order to apply this idea. You can also do this with a syringe, actually. If you fill up a syringe and plug it and then put it in warm or cold water, it will actually change. The plunger will come in and out until it reaches a certain point. So what you can see is a direct proportion. They are directly proportional. So if you increase the temperature of a balloon, its volume increases, and conversely, if you decrease, it decreases. So what we can see is that at high temp, you'll have high volume. At low temp, you'll have low volume, and that looks like that. Okay? Gay-Lussac is pressure and temp, and the example I told one of the classes was that if you're trying to remember this law, the issue of gay marriage was like heated and high pressure for people that it was important to. If that doesn't help, that's fine. The example for Charles was that he was very ticklish, and that's kind of a terrible one, but it does stick with me for some reason. Like maybe the Charlie bit me, maybe that kid. Okay. Good example for pressure and temperature is the aerosol can. We've talked about this already. When you increase the temperature, the particles collide. More forcefully, more frequently. Increasing the force of the collisions, the total overall force, which increases pressure. This is exactly like heating up the gas in a balloon, except the difference is that the container is rigid and its volume can't change, therefore its pressure changes, and then that's it. There's no change in volume subsequently. Okay, and so we can see that when you increase temperature, you increase pressure. They are directly proportional. Oh, I forgot to write the equation to these. Okay, directly proportional. If temperature increases, pressure increases. Temperature decreases, pressure decreases. Okay, and so we have, again, a direct proportion. Okay, so the last question we want to ask ourselves is you can either try to remember the laws or try to intuit what they are. So remember the two options, but from your simulation, you may remember that this was the equation here, which is to say that the product of these two values is a constant. So if one goes up, the other one has to go down in order to maintain that the product of that is one particular number. So that's an inverse relationship, and that's where you get this graph over here. Okay? Conversely, these two have direct proportions. The ratio of them is a constant. It's a little different. So for example, maybe the volume is always a tenth of the temperature. So if you double the temperature, this will have to double also to maintain that relationship. Okay, those are direct relationships. And then again here, just like the other, P1 over T1 will be equal to P2 over T2. Okay, an important thing to remember with all of these is when you plug in temperature, it always needs to be in Kelvin. That's really important. Okay, because otherwise you could have negative temperatures and then it doesn't make sense. None of it makes sense mathematically. You could also have a temperature of 0, which wouldn't make sense. Okay, the combined gas law is basically how do we put these, like what if none of these three variables is constant, is unchanged? So what if you have something like, of course I can't think of an example on the spot. Anyways, something whose volume and temperature and pressure can all change. How do you combine these laws? And basically you just combine them in the way that you would expect them to combine, which is that all the relationships remain intact, but they are all there together. Looks like this. Okay, and it makes sense if T1 is equal to T2. If these two are equal, they would effectively go away, right? Because it would be like dividing both sides by x, and then you have Boyle's law. And the same thing goes if volume is constant, like if this is an aerosol can, then V1 and V2 go away because it's like both things are multiplied by x, and then you have Gay-Lussac's law. So you can see that if you take out one of these variables as a constant, you get each of the three laws, but if none is constant, this is what you get.